regards to what happens when light goes through the glass. Let's start. So the example, okay, they give you a rectangular piece of glass. Okay, this is 2 centimeter wide, okay, or width. They do show you the normal. So they draw you a normal here. And you have light, white light, incoming, like this. All right, from air to glass. So you know what happens. But then they show you as well, or well, actually, you have to remember that on this interface, you're gonna do another, you're gonna draw another normal. All right, like this. Right? And like that. And because you're going from glass to air, you're gonna have light going like this. So this is air, glass, air. And eventually the problem is asking you to find, there are different parts of this problem. You can extend this, and the problem is asking you to find the distance between the final refracted and the extension of the incident, as you can see on your screen. Besides these 2 centimeters, they give you the angle of incidence. That angle is of 37 degrees. And the index of glass in glass equals to 1.36. Quite low, but still. Yeah. Okay, so the first question, an easy one, find the angle of refraction theta. So A, find the angle of refraction theta. Okay, so the angle there. So remember, incident from air to glass, N1 sine theta 1 equals to N2 sine theta 2. Okay, so that's what you have to do for the first part. Now, air, N of air is equal to 1. That's N of glass. So 1 times sine of 37. That's equal to N of glass, 1.36 sine of theta refracted. So 1. So sine of the refracted angle is equal to sine of 37 over 1.36. Okay, so then we can use a calculator to find the angle of refraction. Okay, so that's how we start. So sine of that divided by 1.36. And then we do second 26.3. So I get 26.3 degrees. So that angle here is an angle there. Okay, now remember, this normal is 90 degrees, 90 degrees there, and this normal prime, let's call it, that's also 90 degrees, all right? Okay, now, another question will be, find this length, find this distance, call it y, between the two normals. Find the distance y. You're gonna need it. So you have this angle, right? That's the angle there. So you can redraw this triangle inside like this, where this is 90, this is y, and this is 26.3, right? And you know that that's 2, that's also 2 centimeters. So guys, some questions in exam 3 may need you to remember the basic trigonometry that you did in, well, some of you in 10th grade, some of you probably in senior. It depends on the school, right? But we do this. That's actually something that we teach. And you also should know this, or should have reviewed this in pre-calculus, right? So, opposite of an adjacent equals to the tangent of 26.3. So you can find y. Y is doing 2 times tangent of 26.3. Y equals to 0.99 centimeters, almost 1 centimeter. Okay? So that's the value of y. So why is the problem asking you that? Because the next question is to find the value of b. We're gonna find this value. To find this value, we are going to remember that the distance between two parallel lines is a line perpendicular to both. That's the distance d. This line can be placed anywhere because these are parallel lines. How do I know they are parallel? Because from air to glass to air, the angle here will be parallel to the angle of incidence because you're going back to air. From air to glass to air, you're going back to air. So these lines are parallel. Therefore, this distance can be drawn here. 90. That's there. Okay? And as you can see, there is a right triangle here. I need to find this length. But wait, this length is this one here. That one, this one. And that triangle is this. Let's see if I can draw it. There. 90. That is this. I'm making it bigger here. So this is your D. Okay, that's D. So I need to find this angle here. This angle in here is this angle here. But you do know the value of all this. All this angle is the same as this angle. If you think about it, right? You have to remember, yeah, you're saying that. Vertical angles. This angle is congruent to this angle, right? By vertical angles. So this angle is equal to that. So that's 37. But this angle is 26.3. So this angle here, this angle there is 37 minus 26.3, which is equal to 10.7 degrees. So that's the value of this angle here. This angle is 10.7. And then I need to find this hypotenuse. That's the common hypotenuse for both triangles, right? Well, let's call it H. How do I find H? Using the same. 2 divided by H. Or I can use a Y value, or I can use Pythagorean theorem, right? Yeah, let's use Pythagorean theorem because then we have this. H squared equals to 2 squared plus Y squared, which is this. There. So H is just 2.23 centimeters. That's the hypotenuse. And then I can find D, right? So I have opposite over hypotenuse. So let's use this. Opposite over hypotenuse is equal to sine of 10.7 degrees. Now I can find the value of D. 2.23 times sine of 10.7. So 10.7 sine of that times 2.23. That's 0.41 centimeters. So quite a few things here, right? That's part B here. This will be part C. Part A was just to find the angle of refraction. Part B was to find this length. That then with this, you can find this one here. Why? Because you need the hypotenuse to find the distance between the two rays. Here, this one here. Of course, you need the angle there. So there is some geometry and trigonometry involved. This one here, this trigonometry, to find not just the value of Y and H, but also the value of D. Okay? So the only physics formula, if you think about it, is here. Everything else is geometry and trigonometry. So you need to make sure you practice this. Okay. Like this, it's kind of like the problem that we did at the end yesterday, right? With a prism, where you have to use triangles and angles. So it's kind of the same idea. You have to put in practice some of your geometry and trigonometry. Now, what other questions you can be asked, right? For example, part D is asking you, find the speed of light in glass. Okay? So let's review that. Here, part D. Find the speed of light in glass. If you remember, I said yesterday that the speed of light in any medium V is a speed of light in vacuum, 3 times 10 to the 8, divided by the index of refraction of glass. All right? So this will be 3 times 10 to the 8, speed of light in vacuum, divided by 1.36. So if you use a calculator, you get 2.21 times 10 to the 8 meters per second. All right? So that's another question you are being asked. Okay, so 4 parts for this question here. That's a refraction problem. Let's do a critical angle. This one here. Critical angle, the question is over there. All right, remember we also talked about that yesterday. So how do we use critical angles in certain applications? Periscopes is one application, prisms as well, but there are others. One of those is the one that you're gonna see now. So another way you can apply critical angles is to find the minimum or maximum angle so light doesn't reflect away from a piece of glass or a pipe, right? So in here, for example, you are being given a pipe, a cylindrical pipe like this. And they give you the axis of symmetry. So they give you this. Like that. They give you the incident like that. Theta. And find the maximum angle theta. Critical angle. find the maximum angle theta, so light entering the pipe is total internal reflected. Inside the pipe or inside. What do I mean by that? You're going from air to a pipe that has an index of refraction of 1.35. So you are entering like that from air to glass, like that, right? That's the light inside. But then you want the light to be total internal reflected. So you want light to enter like this, and then go like this, or even like this. So for that, you need a critical angle, but the critical angle is going to happen here. So you have to draw the normal here, or a normal, right? That's 90 degrees. And the angle here, this one has to be theta critical between the material of the pipe and air. So that happens. So there's no refraction. When I have the equation for critical angle there, right? So I can find the critical angle, and then this is a normal. So this is also 90 degrees. I can find the angle here, and here I can use Snell's law, right? So let's write it here. First, let's find the critical angle. So sine of theta critical is N2, which will be air, divided by N1, which is 1.35. So theta critical is sine inverse of that ratio. $47.79. That's the critical angle. People who did a lab today, you know that that's close to what you did, right? That's close to what you guys got in the last experiment. So there you are. Then I can find this angle here. I'm going to call it alpha. So number 2, let's find alpha. In here. How do I find alpha? Theta critical plus alpha is 90 degrees. So alpha is 90 minus theta critical, which is this. Let's just do it here. 42.21. So that's my alpha. So then here, I can do a Snell's law to find the maximum angle theta for that to happen. So then the last thing you have to do is use a Snell's law. So N1 sine theta equals to N2 sine alpha. N1 is air, so the sine theta. N2 is the pipe, 1.35 times sine of alpha, sine of 42.21. Well, let's see. Ooh. So the sine versus that. So 65.09. Okay. Let's try this again so you can see it. This is 1.35 times sine of this angle. All this, sine inverse of this, gives me this angle theta. So that's the maximum angle theta for that to happen. Okay? So multi-step, right? We are using just a couple of equations, but these equations are very important to understand different optical phenomena. Wisdom refraction, critical angles. All right. So now let's see how this is used in lenses. All right. So you see, one of the applications for refraction is lenses, but you're gonna notice that it's more complex than that. Like we work with lenses like we did with mirrors, but it doesn't stop there. There are more applications when we use lenses than mirrors, okay? So some of you are already familiarized with the two types of lenses we're gonna talk about, but most of you are gonna start working with lenses tomorrow here in the lab. Just like with mirrors, there are two types of lenses you have to worry about, or that we're gonna be worrying about. Convergent lens and the divergent lens. In fact, I can show you how they look. So you see, with a mirror, you only have one surface, right? Like this. But with a lens, you have two surfaces, right? This is a convergent lens. Right, one surface, one here. And the divergent lens is like this. Now, be careful because there are other names for this. In the textbook or in other textbooks, well, they call this the convex lens, and they call this the concave lens, or the biconvex lens, and this is a biconcave lens. Regardless, there are a few properties that you have to remember when we start doing problems with lenses, just like with mirrors. It has to do with the signs It has to do with a ray tracing and the definition of a real and virtual image. Because we do have that also in lenses, but it's different than what we did in mirrors. For mirrors, the whole real and virtual was a bit more obvious. Real side is where the object is located. Virtual is behind the mirror. But for lenses, you see, for a lens like this, you can place the object here or here. So then where is the real part? There is not really a real side for a lens, but there is a real image and a virtual image depending on whether you can see the image or not. In the lenses lab, you're going to be using lenses like this, and you're going to be looking at images formed by the lens. These images, if you look at them projected on the screen, they are real. They are real images. So that's the key to understand this. All right? Okay.
Professor?
Yeah.
Before you...
Yeah. Something happened. Hello?
Oh, sorry about that. When you drew the cylinder thing, you put N2 equals 1.35. So wouldn't that be in the numerator, not the denominator?
For this, right?
Yeah.
So since you're going from the pipe to the air,
Yeah.
air will be the second medium, and the pipe will be the first medium.
Yeah, but on the M, like, oh, so you just switched it.
Mm-hmm.
Alrighty, so it doesn't even matter if you wrote N2 equals 1.35.
No, that was the end for the pipe. And when you do the critical angle, that's the thing about the critical angle. You have to be careful from which medium to what medium you are going. If you are going from glass to air, the first medium is glass, the second medium is air. And the other thing that you should know is that there is no critical angle when you are going towards air to glass, air to water. There is only critical angle when you're going the other way around, glass to air, water to air, because of the density of the mediums. The whole idea of critical angle is that there is a maximum incidence where you can see a refracted ray. That happens when you're going from a higher medium to a lower medium. It doesn't happen the other way around.
Thank
okay?
you.
All right. So, lenses. Like yesterday, we're going to start drawing the optical or principal axis here. Okay. And how do you draw a convergent lens? Like that. That's a convergent lens. Okay. This lens has a focal length, F. So, because there are two surfaces, right? The focal point for the lens is located at two places. One and here. So that's the focal. That's the focal point for the lens. Because remember, you can place the object here or here. So it's a and then the radius of curvature, similarly, there. And you can do that also over there. Okay. Right? Okay. So let's suppose I have an object here. That's the object. How is the image of this object formed due to this lens? You're going to use two rays for this. The first ray is the parallel ray to the axis. Like that. And then, as you saw today, some of you, like that. So it's going through the focal point. Goes and then it's like that. It converges, right? It goes through a focal point. The next one is gonna be a ray that goes through the goes like that. Through the lens like that. So they're gonna intersect here. The image is here. So this is what I'm saying. Though. That image, the first thing that you should realize is that it's inverted. But also, if you were to place a screen here, you could see the image. That means that this image is also real. That's a real image. So that changes a little bit, right, from what we talked yesterday. That's because we're dealing with convergent lenses. So convergent lens. For a convergent lens, the focal length is positive always. All right. Okay. So is there a relationship like with mirrors? Yeah. This is the object distance now. P. Well, it's the same before, right? So that's the object distance. And this is the image distance, Q. Or this, you can draw it like this as well. Or that. Right? So, first equation, 1 over P plus 1 over Q equals to 1 over F. Works. Magnification, the same. Height of the image over height of the object, which is negative Q by the P. And image is real if the image distance is positive. There you are. So that's real when the Q is positive. All right. Are there situations where you can get virtual images? Yes. For example, for a divergent lens. The divergent lens, right, always gives you, well, unless you are doing a combination, which we're going to talk about that later. But if it's just the divergent lens by itself, it's always a virtual image. So how does the virtual image look like? Well, let's do the divergent lens, okay? That's the convergent lens. So how do we do the divergent lens? So far, it's similar to mirrors, but some of the size, some of the parameters are a little bit different, so you have to be careful with that. The main thing is that a lens works by refraction and that it has two surfaces. So again, there is no virtual side for a lens per se. All right, so that's the optical axis again. Let's draw the lens. Like that. Like that. So that's the divergent lens. And just like a convergent, it has two focal points. Now, because this is divergent, the focal length is negative, always. Okay? So how do we form images in here? What's the object there? Well, divergent, right? So we draw our parallel ray, and instead of converge, it's gonna diverge like this, but not randomly. It's gonna diverge like this. So this, if you extend the divergent ray, it goes through the focal point, like that. And then we can draw the one that goes through the lens. Like that. So what do you think I found? I found the image. So this is the object. This is the image. The object distance P, the image distance Q. So now the image has formed on the same side as the object. That makes this image virtual. So the image is upright and virtual. Well, always for the divergent length of the case. So the same equations work. And the magnification equation. So that's the case of the divergent and the convergent lens. As I said, there are cases where you may get virtual images also for convergent lenses. How? Easy. Just like the concave mirror. There was a special case, right? So there is also a special case for the convergent lens. Now, you're gonna find that in the problems, instead of calling it convergent lens, they call it a convex lens. So let's write that in here. Convergent are convex lenses. Divergent are concave lenses. It's important to have that. And now we can do problems. All right. The examples for this are more variety. There's more variety for this. We're gonna do first simple lenses problems, and then we're gonna see what happens when you combine this. Because with lenses you can combine. Like you can have a situation where you have this there, and then next to it you have this. We call this a system of lenses. So we can do that. We can actually do that. But for now, let's do the simple stuff first. And then we can go into a more complex scenario. So lenses. Oof. All right, this one here. It says you have a plant. Is 4.1 centimeters tall. And it's located at 10.3. So this is one with decimals, all right? 10.3 centimeters from a convex lens. All right. The image of the plant is 6.2 centimeters tall. So the image of the plant is 6.2 centimeters tall. What's the focal length of the lens? All right. That's the side of the object. That's the size of the image. That's the object distance. They give you the type of lens, convex lens. What is the focal length of the lens? Okay. So let's write here the parameters, the value that we have. P is 10.3 positive. The height of the object is the height of the image is this. And they want you to find the focal. The only way you can find the focal point or the focal length is by using 1 over P plus 1 over Q equals to 1 over F. But wait, I don't have Q, but you have the height. So the magnification is the height of the image over the height of the object. And I have those. 6.2 over 4.1. And what's the magnification also? Negative Q divided by P, which is negative Q divided by 10.3. So I have this equation. 6.2 over 4.1 equals to negative Q over 10.3. So Q will be negative. Why am I sure that Q is negative? Because the magnification is positive. If the magnification is positive, that means that the image is upright and is larger than the object. The image is larger than the object, so it has to be a virtual image. That's why Q is negative. So that will be 10.3 times 6.2 divided by 4.1. That's negative 15.6 centimeters. So that's Q. So I have to be careful, right? Q is negative. So in my equation, 1 over P plus 1 over Q becomes minus 1 over, that's 1 over it. All right. Okay. Guys, you know, if you have decimals like that, finding the common denominator is, well, it's just a multiplication, right? So you should know from math that 1 over f is 15.6 minus 10.3 divided by 15.6 times 10.3. So the focal is when you flip it, 15.6 times 10.3 divided by the subtraction, which is 5.3. So let's see what we get. 30.3 centimeters. So I get a positive focal length. Yes, it's correct. Why? Because it's a convex lens. A convex lens has positive focal length. All right? So the math makes sense. Any questions? All right, let's do another one. So again, so far, right? It's just using the equations of lenses, magnification, kind of like mirrors. All right. Let's do this one now. You have diverging lens. You have a 4-centimeter object here. Which is 50 centimeters from the diverging lens, which has a focal length of negative 25 centimeters. What is the nature and location of the image? So, what is the nature and location of the image? All right. Well, guys, it's a diverging lens. So it's going to be a virtual image. Upright. Right? I mean, if I do the ray tracing, focal length should be around here. Like that. And like that. So that's the image. So it's going to be a virtual upright image. Mathematically, let's check that. We can do that with math. Is indeed. And location, we need to find Q. So 1/50, because that's P, plus 1/the image distance is minus 1/25. You see, you have to be careful with the sign. It's negative there for the diverging lens. So 1/Q equals to negative 1/25 minus 1/50. Well, that one is easy, right? This one you can multiply here by 2. So then you get -2, -1/50. That's 1/Q. So Q is 50/-3. If you flip it, that will be -16.7 centimeters. So yeah, virtual 16.7 centimeters will be this. This is Q. So the image is 16.7 centimeters in front of the mirror. The mirror, the lens. Front of the lens. At the same side as the object. And is virtual upright. Okay? If they were asking you for the height of the image, right? They don't ask you, but let's add that for we do that combination. If you were being asked, what's the height of the image, then you will do this. Height of the image over height of the object, that's the magnification, that's equal to -Q divided by P. The height of the image, that's what you want to find. The height of the object is 4. -Q divided by P, 50. So the height of the image will be 16.7 times 4, should be around 70 something, right? Oh, 66, almost 70, divided by 50, 1.34 centimeters. So yeah, smaller than the object, right? Considering that. All right. Let's do a combination of lenses. All right. because lenses by itself is like mirrors. All right. The problems are similar. You just have to be careful with the signs. Ray tracing helps in some problems, but the applications are more when you combine lenses, especially for divergence, because you can combine lenses to get something more meaningful with divergence. Okay, so let's see what happens when you combine a convergent and a divergent lens. All right. All right. So here, we have a combination here. All right. You have the optical axis like that. All right. And you are given a convergent lens or a convex lens like this. And here. And they give you a few values. For example, that the distance between these lenses is of 1 meter. That the object distance is about 35. About here. So that's the distance, 35. And the focal length of this lens, of the convex lens, is 25. So let's call it F1 is 25. And of the concave, its focal length is -40. So 25 from here. Yeah, right? Yep. And then 40 here. Estimating that right now, F2, F1. Okay. Find the position of the final image produced by the system. So that's the question. Used by the system. All right. Right. So the final image finds position. Look, we want to know the math, but in the problem they give you the figure. So let's use this to show you how to do the image formation when you have two lenses. Okay? For the convergent lens, you have a parallel ray that goes like this, right? And then you have the one that goes to the center. Perfect. There. They intersect there. So, what is this? That is the image due to the first lens. But that's not the final image, because this image is then used by this lens as the object. So this image is the object for this lens. Thus, when you do this image with this lens, this object on that lens, then you find your final image. We can do it. We can continue doing this. So I can use this, and for this to the lens, like that. And then so that's your final image. Clearly, it's going to be virtual, right? And it's going to be inverted respect to that. So we will do the algebra now. We're going to try to make sense of it. Okay? So that's your final image. All right? Okay. So let's label this Q1. This is P1. P1, let's find Q1. Then we're going to find this distance. It's going to be P2. And this is going to be Q2. All right? Okay. So here, 1 over P1 plus 1 over Q1 equals to 1 over 25. So I do the math here. 1 over Q1 equals to 1 over 25 minus 1 over 35. So Q1 will be 35 times 25 over this minus that, 10. So how much is Q1? 35 times 25, 87.5. That's okay. So that's 87.5. So Q1 is 87.5. Like that. But all this distance is 1 meter. Hey, 1 meter is 100 centimeters. So I can find P2. P2 is the object, is the distance between the image due to this lens to the second lens? Well, P2 is 100 minus 87.5, right? It's all this distance minus that distance here. So that's 12.5 centimeters. That's P2. So we're gonna find Q2. To find Q2, we do the lenses equation again, right? 1 over 12.5 plus 1 over Q2 equals to negative 1 over 40. Right? You see that in there? 1 over Q2 is minus 1 over 40 minus 1 over 12.5. So, look, how do you do the math here? The common denominator is 40 times 12.5, but there's negative, minus 12.5 minus 40. That's 1 over Q2. So then Q2 is 40 times 12.5 divided by minus 12.5 minus 40 minus 52.5. All right. Minus negative 9.5. So Q2 is negative 9.5 centimeters. That works. Yeah. So the final image is virtual and 9.5 centimeters in front of the second lens. So it's virtual upright. Forgot to write that, but it's virtual. Okay. What else can you find? You can find the magnification, the overall magnification of this. So how do we find the overall magnification of this image? We have to take into consideration that you have two lenses. So let's do it over there. We're gonna find the overall magnification. The thing about the overall magnification is that you have two lenses. So the total magnification is the magnification due to one lens times the magnification due to the second lens. That is what you have to do. So that's why I left this in here, because we need Q1, P1, P2, and Q2. So we have it here, so we can erase that. This, right? Okay. So the total magnification is for M1, negative P1, sorry, negative Q1, so negative 87.5 over P1 multiplied by negative Q2, but Q2 is negative. So negative 9.5 over P2, 12.5. So we're going to get a negative. Negative and negative, positive, with negative, negative. Yeah, inverted. And then we do the math here. 87.5 times 9.5 divided by 35 divided by 12.5, 1.9. So negative 1.9. So the drawing is not to scale, but it gives you an idea. All right? Give you an idea of how it looks. So that's almost the end of this ray optics. The next idea is to apply this. I'm gonna leave, I was gonna do another refraction problem. I will do it tomorrow. I think it's easier if I do it in person. It will be about apparent height. Okay, we'll do another refraction problem to review that, or maybe a prism. And then we'll do a couple more of this combination of lenses to start doing applications of lenses, which is eye corrective optics. So that's what we're doing tomorrow. For sure, we're finishing that tomorrow. That means that on Monday, we can do a quick review to start doing wave optics, all right? So that will be the last topic for exam 3, wave optics. So I'll let you guys know when what will be the last topic for exam 3. But so far, everything that we have covered, reflection, mirrors, lenses, refraction, all of this, you have to start reviewing, start going on over the assignments 12, 13, and 14, okay? Those are the assignments that cover all this. And then tomorrow we start doing applications of lenses, okay? Are there any questions about this? Okay, let's finish with the attendance as well.
Professor, I joined late. I'm not sure if I got marked absent.
I'm doing it now. That's
Okay.
why I know some of you were late because of the lab. So
Yeah.
all right, it's all updated there. Again, I did it late because some people, and this was gonna happen tomorrow though. So tomorrow we're probably gonna start class at 1:05. This lab is easy but long. It's quite a few experiments. So actually, people who are doing the lab, make sure that you come early, please, so we can start everybody at 11. Okay. Other than that, if you have any questions about your grades, let me know. All the grades have been updated. Just have to grade now labs, but lecture-wise, it should be all good, okay? All right, guys, that's it for today. We'll continue. We'll finish with this tomorrow.